Okay, so here we're going to be working in 8.2 where we start to do hypothesis tests for the mean. The first option that we're going to run in 8.2 is called a z-test. We run the z-test when the population standard deviation is known. If it's unknown, we have to use a t-test, which is what we'll cover in 8.3. The test value is generally calculated as the observed value minus the expected value divided by the standard error. That's a general formula for most of our statistical tests for finding the test value. When we do a z-test, we have to make sure that we use a specific adjustment to that formula. The standard error is calculated by the standard deviation by the square, divided by the square root of n, the number of objects in the sample size. And so there's a small variation of the formula. But if we are using the traditional method, okay, today, which we'll introduce both the traditional method and the p-value method, when we use the traditional method, this is the formula we use to calculate the test statistic. When we are doing hypothesis testing in our traditional method, we start by stating the hypothesis and identifying the hypotheses, the null and the alternative hypothesis that we learned about in 8.1. We're going to identify the claim, which is traditionally the traditionally the alternative hypothesis, but depending on the language of the question, it can be the null hypothesis. Find the critical values from the appropriate table on Appendix C. That's if it's the Z table, we're finding the critical value that creates the cut value. We compute our test value, which is that formula we looked at earlier. We make a decision to reject or not reject the null hypothesis, and we summarize the results. The way we know to reject or not reject the null hypothesis has to do with where the critical regions are, or the rejection regions. Okay? If we find that at alpha equals 0.05, that this line in the sand of some z-score, okay, there's a z-score for the critical value, okay, that everything from that far to the right or that far to the left is going to be in the critical region. And if the test statistic from the specific data lands in these shaded regions, we will reject the null hypothesis. If the z-score for our test statistic lands in this clear or this see-through or white region rather, that section means we do not reject the null hypothesis. So really it's about landing out on these extremes. As we get extreme results, it tells us something must be wrong or different. Let's go through a couple example problems. Example 8.3. A researcher wishes to see if the mean number of days that a basic low-price small automobile sits on a dealer's lot is 29. A sample of 30 automobile dealers has a mean of 30.1 days for basic low-price small automobiles. Okay, so let's start with our null hypothesis. We know, just based on the way this is written, that he seems to believe or thinks that the mean is going to be 29. Now, when we go to write the alternative hypothesis, we're looking for some information. Is it going to be greater than, less than, or not equal to? If we keep reading, it says to test the claim that the mean is greater than 29. So I'm going to go with greater than 29. And because it says to test the claim, that tells me right now that this must be my claim. If I were reading this question and it didn't say test the claim, I would simply say that the researcher was focused on it being equal to 29, and I would make the null hypothesis my claim. But he didn't do that. He very specifically said test this claim. All right, now the next thing I need to do is figure out on my bell curve where the critical values are going to live. Okay, because this is a greater than, it's a right tail test, and because we want alpha at 0.05, that means 0.05 is the area to the right of my critical value. I need to know what that number is that creates the boundary. That's going to be off of my z table, which I'll go back to chapter 7 to find. We're looking for 0.05 to the right, which means if I find 0.05 on the negative side, that I can reflect that. 0.05 would be right here between 0.0505 and 0.0495. When we have to distinguish between two values, we go to the smaller, which makes it 1.65. Go back over here. So this critical value is going to be at a positive 1.65. The next thing I need to do is calculate my test statistic. So for this sample, in the earlier equation, it was x bar, the sample mean, which is 30.1 minus the population mean, or the expected mean, which is 29, and divide that by the standard deviation of 3.8 divided by the square root of the sample size, which was 30 automobile dealers. If I plug that into the calculator and evaluate, okay, I should be able to come up with a number of 1.59. Be careful with your parentheses. You probably 1.59. You should probably put parentheses around the top, parentheses around the bottom, or evaluate the top and bottom individually. That 1.59 in my bell curve over here is going to land before we get to 165. So that would be a non-rejection region. So the next step would be to make a decision, okay? And we will not reject the null hypothesis. We weren't in the rejection region. We're not far enough or extreme enough. So to summarize, we're going to say that there is not enough evidence to support the claim. Okay. If it's in the alternative hypothesis, we're going to use the word support. Okay. We could have enough evidence to support the claim if we're in the shaded region, or we cannot have enough evidence to support the claim. If we're in the null hypothesis, it's always about reject. So we could, if the claim was that it was 29, if the null hypothesis was the claim, then I could say that there was not enough evidence to reject the null hypothesis and reject the claim. So if it's in the alternative hypothesis, we either support, because we always use support. There's either enough evidence to support it or there's not enough evidence to support it. If it's in the null hypothesis, there's either enough evidence to reject or not enough evidence to reject. So the language there is very specific and particular. Let's look at another example along the way. If we did this one, we've already got the null and alternative hypothesis set up. Okay, you can pause it and read through the question. If I have these as my two hypotheses, I need to kind of come up with my critical values. And because it's a not equal to, I'm going to have two tails. Okay. If alpha is listed at 0.01, then a tail is going to have half of that, or 0.005 and 0.005. Okay, half and half when it's a two-tailed test. If I go back to chapter 7 and look at my table, here at 2.5, 7 and 8, I see these numbers, 0.0051 and 0.0049. Again, when we're evenly split, we go to the smaller value in the tail. So this is going to put us at 2.58. That's both positive and negative. So if I come back here, negative 2.58 and a positive 2.58. I now need to find my test statistic. The z for this specific problem would be 26,343 minus 672 divided by standard deviation of 3251 divided by the square root of our sample size, which is 35 stroke victims. If we evaluate our problem, we should get 3.04, which would land over here in the rejection region, leading me to make the decision to reject the null hypothesis. If the claim, okay, was that it's not equal, then we can say there is enough evidence to support the claim. Okay. There is another method that's going to allow us to use our calculator and use technology to help aid the process, and it will actually speed things up quite a bit. When we use a p-value method, the p-value represents the probability of incorrectly rejecting the null hypothesis. And if the p-value is less than or equal to alpha, we can choose to reject the null hypothesis. I don't have to scan through a chart. I don't have to go searching for specific numbers. The calculator is going to give me a p-value, that all I have to do is compare it to alpha, which is going to be given in the initial conditions. This test value here is going to be what we calculate in the calculator, is what we're going to use based on alpha. Okay, the p-value is our value that the calculator is going to produce for us, and we'll make a decision and deal with the results. So here's another example problem. This time we'll use the p-value method in our calculator, and I'll show you how it saves a bunch of time. Wants to make these claims. You can read through that. Hopefully this makes sense why the null hypothesis is that mu is 5700 and the alternative hypothesis is that it's greater than 5700 with that as a claim. What we're going to do now is we're going to go straight to the calculator. We're going to press stat, go to our tests, and we're going to run a z-test. I'm going to do it based on statistics with a mean, an initial mean of 5700. That'll always be your null hypothesis. My standard deviation is 659. The sample mean from the sample we took is 5950, and that was a sample of 36. I could choose not equal to, I could choose less than, I could choose greater than. I'm going to go ahead and choose greater than because that is the symbol that's there. I'm going to go ahead and choose to calculate. Now this gives me a z-score of 2.276, right? So my test statistic would be z equals 2.28. Okay. Whoops. Z equals 2.28. But that doesn't really help me. What I really want is the p-value. P-value. And the p-value on this problem is listed as 0.011. Now, if we're using an alpha of 0.05, you can see how this 0.011 is less than alpha. Therefore, we are going to reject the null hypothesis. Essentially, what you can think of this as is if we had a bell curve, and if 0.05 was right there, the question is, where would the 0.11 be? Well, 0.11 would be further over. 0.011, sorry. Because it's smaller, it would be further to the tail. We can see that lands in the rejection region. Okay. So that being said, we would know that we're going to reject the null hypothesis, and we would say, there is enough evidence to support the claim. The big thing with this is understanding, hey, I can go straight to the calculator. All I really need is that p-value and my alpha. I don't have to draw a graph. I just need to be able to make the decision. If the p-value is smaller than alpha, I reject. If the p-value is bigger than alpha, I fail to reject, or I don't reject. Hopefully that helps you, and whatever questions you have, just come into class and ask. All right, see ya.